In fluid dynamics, wind waves are surface waves that occur on the free surface of oceans, seas, lakes, rivers, and canals, or even on small puddles and ponds. They result from the wind blowing over an area of fluid surface. Waves in the oceans can travel thousands of miles before reaching land. Wind waves range in size from small ripples to 30 m high. When directly generated and affected by local winds, a wind wave system is called a wind sea. After the wind ceases to blow, wind waves are called swells. More generally, a swell consists of wind-generated waves that are not usually affected by the local wind at that time. They have been generated elsewhere or some time ago. Wind waves in the ocean are called ocean surface waves. Wind waves have a certain amount of randomness. Subsequent waves differ in height, duration, and shape with limited predictability. They can be described as a stochastic process, in combination with the physics governing their generation, growth, propagation and decay as well as governing the interdependence between flow quantities such as the water surface movements, flow velocities and water pressure. The key statistics of wind waves in evolving sea states can be predicted with wind wave models. Although waves are usually considered in the water seas of Earth, the hydrocarbon seas of Titan may also have wind-driven waves. Wave formation. The great majority of large breakers one observes on a beach result from distant winds. 5 factors influence the formation of wind waves: wind speed or strength relative to wave speed. The wind must be moving faster than the wave crest for energy transfer. The uninterrupted distance of open water over which the wind blows without significant change in direction, width of area affected by fetch, wind duration, the time over which the wind has blown over a given area, water depth, all of these factors work together to determine the size of wind waves, wave height, wavelength, wave period, wave propagation direction. A fully developed sea has the maximum wave size theoretically possible for a wind of a specific strength, duration, and fetch. Further exposure to that specific wind could only cause a loss of energy due to the breaking of wave tops and formation of white caps. Waves in a given area typically have a range of heights. For weather reporting and for scientific analysis of wind wave statistics, their characteristic height over a period of time is usually expressed as significant wave height. This figure represents an average height of the highest one-third of the waves in a given time period, or in a specific wave or storm system. The significant wave height is also the value a trained observer would estimate from visual observation of a sea state. Given the variability of wave height, the largest individual waves are likely to be somewhat less than twice the reported significant wave height for a particular day or storm. Sources of wind wave generation. Seawater wave is generated by many kinds of disturbances such as seismic events, gravity, and crossing wind. The generation of wind wave is initiated by the disturbances of cross-wind field on the surface of the seawater. 2 major mechanisms of surface wave formation by winds and other sources of wave formation can explain the generation of wind waves. However, if one set a flat water surface and abrupt cross-wind flows on the surface of the water, then the generation of surface wind waves can be explained by following 2 mechanisms which initiated by normal pressure fluctuations of turbulent winds and parallel wind shear flows. The mechanism of the surface wave generation by winds. 1. Starts from OE fluctuations of wind. The wind wave formation on water surface by wind is started by a random distribution of normal pressure acting on the water from the wind. By the mechanism developed by O.M. Phillips, the water surface is initially at rest and the generation of wave is initiated by adding turbulent wind flows and then, by the fluctuations of the wind, normal pressure acting on the water surface. This pressure fluctuation arises normal and tangential stresses to the surface water, and generates wave behavior on the water surface. Assumptions 1. Water originally at rest 2. Water is inviscid 3. Water is irrotational 4. Random distribution of normal pressure to the water surface from the turbulent wind 5. Correlations between air and water motions are neglected. 2. Starts from wind shear force on the water surface. John W. Miles suggested a surface wave generation mechanism which is initiated by turbulent wind shear flows y, based on the inviscid or Sommerfeld equation in 1957. He found the energy transferred from wind to water surface as a wave speed, c is proportional to the curvature of the velocity profile of wind unregistered trademark unregistered trademark, y, at point where the mean wind speed is equal to the wave speed. Since the wind profile y, is logarithmic to the water surface, the curvature unregistered trademark unregistered trademark, y, have negative sign at the point of y equals c. This relations show the wind flow transferring its kinetic energy to the water surface at their interface, and arises wave speed, c. The growth rate can be determined by the curvature of the wind/dz2 at the steering height equals c, for a given wind speed way assumptions. 1. 2D parallel shear flow, y, 2 incompressible, inviscid water/wind 3 irrotational water 4. Slope the displacement of surface is small, a eurocent generally. These wave formation mechanisms occur together on the ocean surface and arise wind waves and grows up to the fully developed waves. For example, if we suppose a very flat sea surface, and sudden wind flow blows steadily across the sea surface, physical wave generation process will be like 1. Turbulent wind flows form random pressure fluctuations at the sea surface. Small waves with a few centimeters order of wavelengths is generated by the pressure fluctuations. 2. The crosswind keep acting on the initially fluctuated sea surface, then the wave become larger. As the wave become larger, the pressure differences get larger along to the wave growing, then the wave growth rate is getting faster. Then the shear instability expedites the wave growing exponentially. 3. The interactions between the waves on the surface generate longer waves and the interaction will transfer wave energy from the shorter waves generated by the Miles mechanism to the waves of slightly lower frequencies than the frequency at the peak wave magnitudes, then finally the waves will be faster than the crosswind speed. Note: most of the wave speeds calculated from the wavelength divided by the period are proportional to sq or t. Thus, except for the shortest wavelength, the waves follow the deep water theory described in the next section. The 28 feet long wave must be either in shallow water or between deep and shallow. Types of wind waves. 3 different types of wind waves develop over time: capillary waves, or ripples, seas, swells. Ripples appear on smooth water when the wind blows, but will die quickly if the wind stops. The restoring force that allows them to propagate is surface tension. Seas are the larger scale, often irregular motions that form under sustained winds. These waves tend to last much longer, even after the wind has died, and the restoring force that allows them to propagate is gravity. As waves propagate away from their area of origin, they naturally separate into groups of common direction and wavelength. The sets of waves formed in this way are known as swells. Individual rogue waves much higher than the other waves in the sea state can occur. In the case of the Draupner wave, its 25 am height was 2.2 times the significant wave height. Such waves are distinct from tides, caused by the Moon and Sun's gravitational pull, tsunamis that are caused by underwater earthquakes or landslides, and waves generated by underwater explosions or the fall of meteorites all having far longer wavelengths than wind waves. Yet, the largest ever recorded wind waves are commonly not rogue waves in extreme sea states. For example, 29.1 am high waves have been recorded on the RRS Discovery in a sea with 18.5 am significant wave height, so the highest wave is only 1.6 times the significant wave height. The biggest recorded by a buoy was 32.3 am high during the 2007 Typhoon Nekroza near Taiwan. Ocean waves can be classified based on the disturbing force, S, that create, them. The extent to which the disturbing force, S, continue, S, to influence them after formation. The extent to which the restoring force, S, weaken, S, them. And their wavelength or period. Seismic sea waves have a period of 20 minutes, and speeds of 760 km per hour. Wind waves have a period of about 20 seconds. The speed of all ocean waves is controlled by gravity, wavelength, and water depth. Most characteristics of ocean waves depend on the relationship between their wavelength and water depth. Wavelength determines the size of the orbits of water molecules within a wave, but water depth determines the shape of the orbits. The paths of water molecules in a wind wave are circular only when the wave is traveling in deep water. A wave cannot feel the bottom when it moves through water deeper than half its wavelength because too little wave energy is contained in the small circles below that depth. Waves moving through water deeper than half their wavelength are known as deep water waves. On the other hand, the orbits of water molecules in waves moving through shallow water are flattened by the proximity of the sea surface bottom. Waves in water shallower than 1/20 their original wavelength are known as shallow water waves. Transitional waves travel through water deeper than 1/20 their original wavelength but shallower than half their original wavelength. In general, the longer the wavelength, the faster the wave energy will move through the water. For deep water waves, this relationship is represented with the following formula. Where c is speed, L is wavelength, and t is time, or period. The speed of a deep water wave may also be approximated by where g is the acceleration due to gravity, 9.8 meters per second squared. Because g and I are constants, the equation can be reduced to when c is measured in meters per second and L in meters. Note that in both instances that wave speed is proportional to wavelength. The speed of shallow water waves is described by a different equation that may be written as where c is speed, g is the acceleration due to gravity, and d is the depth of the water. The period of a wave remains unchanged regardless of the depth of water through which it is moving. As deep water waves enter the shallows and feel the bottom, however, their speed is reduced and their crests bunch up, so their wavelength shortens. Wave shoaling and refraction. As waves travel from deep to shallow water, their shape alters. This process is called shoaling. Wave refraction is the process by which wave crests realign themselves as a result of decreasing water depths. Varying depths along a wave crest cause the crest to travel at different phase speeds, with those parts of the wave in deeper water moving faster than those in shallow water. This process continues until the crests become parallel to the depth contours. Razor lines normal to wave crests between which a fixed amount of energy flux is contained converge on local shallows and shoals. Therefore, the wave energy between rays is concentrated as they converge, with a resulting increase in wave height. Because these effects are related to a spatial variation in the phase speed, and because the phase speed also changes with the ambient current due to the Doppler shift the same effects of refraction and altering wave height also occur due to current variations. In the case of meeting an adverse current, the wave steepens, that is, its wave height increases while the wavelength decreases, similar to the shoaling when the water depth decreases. Wave breaking. Some waves undergo a phenomenon called breaking. A breaking wave is one whose base can no longer support its top, causing it to collapse. A wave breaks when it runs into shallow water, or when two wave systems oppose and combine forces. When the slope, or steepness ratio, of a wave is too great, breaking is inevitable. Individual waves in deep water break when the wave stiffness the ratio of the wave height h to the wavelength ia exceeds about 0.07, so for Ha 0.07 ai. In shallow water, with the water depth small compared to the wavelength, the individual waves break when their wave height h is larger than 0.8 times the water depth h, that is Ha 0.8 ah. Waves can also break if the wind grows strong enough to blow the crest off the base of the wave. Three main types of breaking waves are identified by surfers or surf lifesavers. Their varying characteristics make them more or less suitable for surfing, and present different dangers. Spilling, or rolling, these are the safest waves on which to surf. They can be found in most areas with relatively flat shorelines. They are the most common type of shorebreak, plunging, or dumping. These break suddenly and can dump swimmers pushing them to the bottom with great force. These are the preferred waves for experienced surfers. Strong offshore winds and long wave periods can cause dumpers. They are often found where there is a sudden rise in the sea floor, such as a reef or sandbar. Surging, these may never actually break as they approach the water's edge, as the water below them is very deep. They tend to form on steep shorelines. These waves can knock swimmers over and drag them back into deeper water. Science of waves. Wind waves are mechanical waves that propagate along the interface between water and air. The restoring force is provided by gravity, and so they are often referred to as surface gravity waves. As the wind blows, pressure and friction forces perturb the equilibrium of the water surface. These forces transfer energy from the air to the water, forming waves. The initial formation of waves by the wind is described in the theory of Phillips from 1957, and the subsequent growth of the small waves has been modeled by Miles, also in 1957. In the case of monochromatic linear plane waves in deep water, particles near the surface move in circular paths, making wind waves a combination of longitudinal and transverse wave motions. When waves propagate in shallow water, the particle trajectories are compressed into ellipses. As the wave amplitude increases, the particle paths no longer form closed orbits. Rather, after the passage of each crest, particles are displaced slightly from their previous positions, a phenomenon known as Stokes drift. As the depth below the free surface increases, the radius of the circular motion decreases. At a depth equal to half the wavelength I, the orbital movement has decayed to less than 5% of its value at the surface. The phase speed of a surface gravity wave is a for pure periodic wave motion of small amplitude waves a well approximated by where c equals phase speed, I equals wavelength, d equals water depth, g equals acceleration due to gravity at the Earth's surface. In deep water, where so and the hyperbolic tangent approaches, the speed approximates in SI units, within ms, when is measured in meters. This expression tells us that waves of different wavelengths travel at different speeds. The fastest waves in a storm are the ones with the longest wavelength. As a result, after a storm, the first waves to arrive on the coast are the long wavelength swells. For intermediate and shallow water, the Bus-Einstein equations are applicable, combining frequency dispersion and nonlinear effects. And in very shallow water, the shallow water equations can be used. If the wavelength is very long compared to the water depth, the phase speed can be approximated by. On the other hand, for very short wavelengths, surface tension plays an important role in the phase speed of these gravity capillary waves can be approximated by where S equals surface tension of the air-water interface equals density of the water. When several wave trains are present, as is always the case in nature, the waves form groups. In deep water the groups travel at a group velocity which is half of the phase speed. Following a single wave in a group, one can see the wave appearing at the back of the group, growing and finally disappearing at the front of the group. As the water depth decreases towards the coast, this will have an effect. Wave height changes due to wave shoaling and refraction. As the wave height increases, the wave may become unstable when the crest of the wave moves faster than the trough. This causes surf, a breaking of the waves. The movement of wind waves can be captured by wave energy devices. The energy density of regular sinusoidal waves depends on the water density, gravity acceleration and the wave height. The velocity of propagation of this energy is the group velocity. Wind wave models. Surfers are very interested in the wave forecasts. There are many websites that provide predictions of the surf quality for the upcoming days and weeks. Wind wave models are driven by more general weather models that predict the winds and pressures over the oceans, seas and lakes. Wind wave models are also an important part of examining the impact of shore protection and beach nourishment proposals. For many beach areas there is only patchy information about the wave climate, therefore estimating the effect of wind waves is important for managing littoral environments. Seismic signals. Ocean water waves generate land seismic waves that propagate hundreds of kilometers into the land. These seismic signals usually have the period of 6 AA plus or minus A2 seconds. Such recordings were first reported and understood in about 1900. There are two types of seismic ocean waves. The primary waves are generated in shallow waters by direct water-wave-land interaction and have the same period as the water waves. The more powerful secondary waves are generated by the superposition of ocean waves of equal period traveling in opposite directions, thus generating standing gravity waves with an associated pressure oscillation at half the period, which is not diminishing with depth. The theory for microseism generation by standing waves was provided by Michael Longuet-Higgins in 1950, after in 1941 Pierre Bernard suggested this relation with standing waves on the basis of observations. Internal waves can form at the boundary between water layers of different densities. These subsurface waves are called internal waves. As is the case with ocean waves at the air-ocean interface, internal waves possess troughs, crests, wavelength, and period. Internal waves move very slowly because the density difference between the joined media is very small. Internal waves occur in the ocean at the base of the pycnocline, especially at the bottom edge of a steep thermocline. The wave height of internal waves may be greater than 30 meters, causing the pycnocline to undulate slowly through a considerable depth. Their wavelength often exceeds 0.8 kilometers and their periods are typically 5 to 8 minutes. Internal waves are generated by wind energy, tidal energy, and ocean currents. Surface manifestations of internal waves have been photographed from space. Internal waves may mix nutrients into surface water and trigger plankton blooms. They can also affect submarines and oil platforms. Other types of ocean waves, tidal waves. The only true tidal waves are relatively harmless waves associated with the tides. Tsunami and storm surges are sometimes referred to as tidal waves in popular writing. Storm surge, the abrupt bulge of water driven ashore by a tropical cyclone, is called a storm surge. Tsunami, a long wavelength, shallow water progressive waves caused by the rapid displacement of ocean water are called tsunami. Tsunami caused by the sudden, vertical movement of Earth along faults are properly called seismic sea waves. Tsunami can also be caused by landslides, icebergs falling from glaciers, volcanic eruptions, asteroid impacts, and other direct displacements of the water surface. All seismic sea waves are tsunami, but not all tsunami are seismic sea waves. The speed of a tsunami is given by the formula for the speed of a shallow water wave. See also, notes. References, Scientific, Stokes, G.G. on the Theory of Oscillatory Waves. Transactions of the Cambridge Philosophical Society 8, 441 €455, reprinted in, G.G. Stokes. Mathematical and Physical Papers, Volume I, Cambridge University Press, ppA 197 €229. Phillips, O.M. The Dynamics of the Upper Ocean. Cambridge University Press. ISBN A0-521-29801-6. Holthusen, Leo H. Waves in Oceanic and Coastal Waters. Cambridge University Press. ISBN A0-521-86028-8. Jensen, Peter. The Interaction of Ocean Waves and Wind. Cambridge University Press. ISBN A978-0-521-46540-3. Other, Razmanier, John. The Annapolis Book of Seamanship. Simon & Schuster. ISBN A0-671-67447-1. Carr, Michael. Understanding Waves. Sale, 38 €45. External links, Anatomy of a Wave. Holborn, J. Boatsafe.com. Captured 506, NOAA National Weather Service, ESA press release on swell tracking with ASA onboard ENVISAT, Introductory Oceanography Chapter 10 Ocean Waves, Hyperphysics Ocean Waves.